in these sections, I will review again the bending stress, and then also kind of come up with the other terms that you need to know from the textbook. And so there's 4 items. Basically, it's my preferred methods for determining the bending stress. Then the section modulus and engineering beams, appendix C, those are the 3 items, and I think you need to know. And let us first review the calculations of the bending stress. And so basically here we look at the beam and with the symmetric cross sections. Here I showing is a trapezoidal. This is basically for this pair of the moment is going to curve up the beam and something like this one here. So basically in tendency on the any cross sections, and that is the distribution of the bending stress, because this curve up we know upper portion is in compression, lower portion is in tension. So basically here kind of showing you more kind of like this. And before deform, the cross section will be like the dash lines, the kind of the section here, and then after bending, curve up, the upper portion basically linked toward the center here, the lower portion basically stretch out here. Okay, so something like this one. So in this way, by looking at this figure here, you could see the material point in the upper portion is compressed into, and then that basically is in compression, lower portion is stretched out, that is in tension here. And then on the other side, if we if we look at from the cross sections side, okay, in terms of this figure basically showing in this diagram here, okay. And many times we kind of do more often, and for you right now our experience in determining the bending stress, so it's more convenient, and we kind of work directly on the determine the bending stress on the cross section here. So you will see more often and often we will more likely to work on the cross section viewpoint rather than this or this. Again, we will be more likely and convenient to work on the cross-section viewpoint to determine to calculate the bending stress. Okay, so under these situations, then here again using we applied our right hand rule and put your 4 fingers in the circulations of the the bending, and then the direction of your thumb basically pointing to is the double arrow direction. So here is a double arrow direction, so that's showing on the cross section here. This cross section basically is viewing from these directions. Okay, so this cross section, in this way I translate the double arrow sign to here, that is the direction here. So again from this case I translated, and you apply your sum of rule, the right hand rule, then you can see the 4 fingers basically when you align your thumb to the double arrow direction, your 4 finger basically point into, and that kind of have a tendency to push the material into this paper, and that kind of producing the compression. So this provides you another way to quickly identify where in the cross section is under compression. And then again the lower portion here is again have the way to out of the paper, so that's just like in showing here under the tension, so that is in tension here. So this is a way to determine the attribute, which means the tension, compression, and then the remaining is on the different determination of the magnitude of the bending stress. The magnitude of bending stress is I use this symbol, and you will see this symbol in our textbook. This simply is to ignore the older signs for all the terms, basically whatever the magnitude for m, and the y is a distance. For example, if say you want to determine the stress here, you simply measure what is the distance between this one, that is give you the value of y here, and I is a moment of inertia with respect to the neutral axis. Okay, so y is a moment of inertia with respect to the neutral axis. So that is I preferred. I try to disengage the determination of the tension compression from the calculation of the magnitude. I think in my personal experience, this is easier. And let's look at another, review this concept one more time. So this basically, this is the beam is on the bending, and this one is to curve down. So the beam will be curved down like this. Okay, so let me draw like this one here. So that's a curve down here. And then this is the neutral surface, and here in this way the material point on the top portion, due to this we understood the distribution of the bending stress will be like this. So in the upper portion, material is kind of stretched, and then so that is in tension, and the lower portion is in compression. And again, this is the neutral surface, and then here we translate that information to here, so that's a negative. Okay, so again, let's work on the cross-section viewpoint. So again, apply your right hand rule. So basically you can see the double arrow direction should be pointing to that direction. Okay, so again, this cross-section here viewing basically is we look at from this viewpoint to extract this cross-section. So for example, this is the y direction and this is the z direction. Let me translate that one here. So that is the direction here. So basically here is our double arrow direction for moment. Okay, so again, right now apply the right hand rule. So from this, for this case, you can see your 4 fingers pointing into the papers at the lower portion, so that is have a tendency to push the material points into the paper and in the kind of showing like this way. So basically that get a shortened fiber there. So we conclude this is in compression, and the upper portion on the other side is opposite to here is in tension. So this is a way to determine the attribute about the where is in tension, where is in compression of the cross section. And again, back to the magnitude. So magnitude simply is calculate the my over I. So again, if you want to determine the bending stress here, you simply measure the distance, and that gives you the y, and you put into here. M is the magnitude given by the problem statement. I again is the moment of inertia respecting the neutral axis. Okay, so that is the preferred method I kind of suggest to you. And okay, in this slide, I want to introduce the elastic section modulus, and sometimes the people simply call this section modulus. And that one simply is a quantity that is the dimensions, geometric related quantity respect to the cross section. Basically, that definition is this: the maximum bending stress, okay, and that can be calculated by M divided by S. S is our section modulus. So we are given the magnitude of the bending, and given any material, we can look up the data book for the section modulus and corresponding to the beam, the type of beam we select. And so from here, this is a given loading, and this is a given from the material data book. Then right away we can predict the maximum stress. Okay, so that's a way to how to utilize the section modulus. So this section modulus basically application is this: given a moment, if we, for our design, if we wish to have a smaller the maximum bending stress, then for our selection, we better to select a beam which has a larger value of S. Okay, so that is the applications stay here. So we can look at one example here. So consider we have considered 2 rectangular cross section of the same area. So this rectangle has the area 24 inches square, the same thing like this one. And for this case, we want to know which one has a larger section, the section modulus S, okay? So we can see from here, we know the S equal to I divided by S by the C, okay? C is the distance per this notation for this example. C is the distance from neutral surface to where the maximum stress occurred. Okay, this is the maximum stress occurred. So basically for this case, you can see this is our neutral axis. C is the half of H. Okay, so C equal to half of H. So here C equal to half of H, and I is a moment of inertia. Say this is the neutral axis here. So basically that one is equal to 112 and B times H cube. So that's I. So we do the calculation here. So basically it's 16 and BH squared. Okay, so then let me do a little bit more derivation. Is 16 and then that is BH and times H. Okay, so from here, because BH is the A, so that is A divided by 6 times H. For the two rectangular cross section, they have the same edge. They have the same area here. So from here, you can see this one has a larger S. Okay, this one has a larger S because S for this case is proportional to the height here. So this one has a larger S. So which means if you're going to use to pick a beam for design purposes, then you better to pick this one because this one gives you a larger sectional modulus S. This one likely will give you the bending stress that is the smaller than this will have. Okay. So that is the one, and here I come to is the kind of introductions of the more practical discussion, the generals, the beam, we call the S beam or W beam. Those are kind of the standard, the specification that common in industry. And we have S beam, we have W beam, we have other type of beam. And because for manufacturing, they come up with the very detailed the geometry and dimension specifications. So usually it come up with a table. So this table I grab is from part of the Appendix C in the textbook. Okay, so for example, this is for S beam, S shape. So that gives you the connection. So that is the for example catalog number or whatever. So for this, for example, we can look at more detail. For this specific beam, it has the cross-sectional area that big, and it has the depth D per the definition, and flange, that means the top or the bottom here. Okay, it has BF and B, whatever the dimensions. And for web, and that's the middle portion, it has the given dimension. And here come to is the derived quantity. This is the good side of this table. So basically from this table, you can right away access to the moment of inertia respect to this axis or y-axis, depends on your loading conditions. And then this is the sectional modulus. Okay, so everything is kind of given in this table, and so that is a very practical kind of application, kind of providing to you. And so this one, I think this one or I think one or two kind of homework example kind of designed regarding how to kind of guide you to apply this table for kind of calculations here. Okay, so now let's go to the different topic. So here again, we remind you when before we derive the quantities, we have this one derive the moment given the magnitude of the moment can be related to the radius of a curvature. Again, this is the radius of curvature measuring from the common center to neutral surface. Okay, and this is called the radius of curvature, and 1 over rho simply equal the curvature. Okay, so curvature is proportional to magnitude of the bending. Okay, so the larger the bending, you're going to curve more of the beam, which means the beam have a larger curvature here. And the proportionality basically is given by EI. EI times the curvature of the beam. So many times we kind of combine this term together, EI over. Okay, so this is similar to this in our chapter 2 or in Hooke's law or whatever the things. In here we and in Hooke's law we know that F equal to K times delta spring constant multiply with deformation or displacement. Okay, so this is the given loading. So the similar concept is like this. The given loading in terms of a moment is m equal to the curvature. Basically you can visualize as the deformation is a description of describing the deformed beam. Okay, and then the corresponding the spring constant, basically the rho of the K of the EI basically have the similar role as playing with the K. So from here it's kind of get clear. We have the given loading, we have the way to describe the deformation, then the EI simply is equivalent, I would say kind of equivalent spring constant for this system here. Okay. And this is the last topic I want to introduce quickly. And here this is the we kind of draw the three-dimensional deformation of the beam, and this beam is curved up. Okay, and here we want to talk about the influence of the Poisson ratio. The Poisson ratio basically is a way to induce the lateral deformation. So when we curve up, then this is the beam. Okay, this is the neutral surface. When the beam is curving up like this is the neutral surface. And we know in the upper portions, this one is under compressions. Okay, so let me translate the information here. So in the upper portion, that is under compression. So under compression, that means it's compressed. And then if we multiply the corresponding strength with the Poisson ratio, we know if one direction is compressed, then in the lateral direction it should be widened, because that's due to Poisson ratio effect. Okay, so in the z direction, in the y direction, we have the same effect basically given by this. So translating the information into the lateral direction, we have this, we call the lateral, the curvature, radius of curvature in the lateral directions. Okay, and then here we define this quantity basically is the, we call the anti-clastic, the curvature. So basically that describing is the curvature corresponding in the lateral direction. So this one just kind of give you the concept. And before these slides, we always talk about it's one-dimensional, but with the Poisson ratio effects being introduced, then everything can be into three-dimensional. And this one only have the concept here will be good enough, and then I won't emphasize too much in the three-dimensional bending, because that will be more belonging to the more advanced topic here. Okay, but here again you just have the concept here, that'll be good enough.